Hello. So this time we will look into this problem and try to solve it. So we are given the tree in the way that, for example, we have something like that, and all these points are vertices of the tree. Then we have numeration of all of these vertices. 1, 2, 3, 4. And once we delete any of the edges, we write the maximum number in each part. For example, if I delete this vertex, then in the left side I have the maximum number is 1. On the right side the maximum number is 4. So I will have 1, 4. If I delete this edge, on the left side, the maximum number will be 2. On the right side, the maximum number will be 4. And if I delete this edge, on the left side, the maximum number will be 3. And on the right side, the maximum number will be 4. This is the description of our tree. So our task is to reconstruct the tree from this description. So let's note one thing. It doesn't matter what is the shape of our tree. When we divide it onto two halves, so for example, we have this half and this part. So there were many edges, and we deleted only one of them that connected them. So here we had some edges, here we had some edges. So when we delete them, either left or right part has the maximum number. So we have vertices 1 to n, and the vertex n must be either on the left or on the right. So all our outputs must contain number n. Thus, we only need to look here in the example of inputs, we only need to look on the one number out of 2. So we check that the second number must be the maximum number. It might be the first number or second number in the pair, but we must check that there is the maximum number over there. So if there is no such number, then the input is incorrect. So we answer no in this case. For example, if we have like n is equal 4 and we have input 1, 2. So we don't have 4 here. It means this is incorrect input. We cannot reconstruct such tree. One of the numbers must be the maximum number. So this is the one way to check it. Next, we checked everything. So in each pair we have one number n and another number is not n. So what we do with these numbers? Well, if I decompose anything, I can, for example, write n equal 4, and I will write 3, 4, 3, 4, 3, 4. Is it possible to have such tree? Yes, it is. So we start with number 3 and we end with number 4. All the edges will go like that. And the numbers between will be 1 and 2. So if I delete any of the edges, one part will have maximum of 3 and another part will have maximum of 4. So what exactly means that we have this 3-4 pair 3 times? 3 times. What does it mean? Well, it means distance between 3 and 4. Okay, so we understand that if we have 4 as a maximum number and then 3, one number minus, yes, one less than the maximum number, then the number of times it appears is the distance between 3 and 4. Let's move to another example. Let's say I have n minus 1 n minus 1 n, so twice. Then I have n minus 2 n, n minus 2 n, n minus 2 n. So I have this sequence, and then neither of n minus 1 or n minus 2 appears. So only 3 times we have n minus 2. Only twice we have n minus 1. So from the previous example, we know that we have n minus 1, then 1 vertex, and then n. Then we have n minus 2 3 times. What does it mean? It means that the distance from this path from n minus 1 to n is 3 to the n minus 2. So we have 1, 2, and then we have n minus 2. So the tree will look like that. However, we said that this is the distance between this vertex and this path. We do not say where exactly this path, new path to n minus 2, connects to the old path from n minus 1 to n. It might connect here, it might connect here. So now we move on to the real solution. So what we do to solve this problem? So we have a lot of n, 1n, maybe 3n, etc. Then we check how many times each of them appears in the list. For example, let's imagine we have 1n twice. It means that the distance from 1 to n is 2. But it also means that here we must have some vertex. And when I cut this edge, the maximum to the left must be 1. But if the maximum to the left is 1, here we must have 0. But 0 is not allowed. So what does it mean? It means that each number must appear no more than itself. So 1 must appear not more than 1. 2n must appear no more than twice. 3n must appear no more than 3 times, etc. It's our second checking. So if we don't have this rule followed, we answer no. So we counted every our pair, our number, how many times they appear. Then we start from the smallest number. So we start from the smallest number. It might not be 1. 1 might not be appearing there. For example, we might have 4, 1. So what does it mean? We put 4, we look which number goes next. For example, next number is 61. It must connect from 4 to 6 using distance 1, so only one edge. Then we might have 6n twice, and for example 9n. It means that from 6 to 9 we can have two edges, and here we will have 9. What is the number between 6 and 9? Any number smaller than 6 that we didn't use yet. So we didn't use 1. We put 1 here. So we have some array where we remember which numbers we used. And we have pointer at the smallest number that we didn't use yet. So once we use this number, we move pointer to the next one. If we, for example, put 6 and 4, we put like 6, then we already used them. So we cannot use them any further. So we put here 1, we used 1. Next thing, we construct another one. As I told in the beginning, that we could attach a new path to any vertex in the old path. It means that we have the ability to reconstruct our tree as a single line. So the answer to this task will be something like that: single line ending with n. Because no matter how we cut our edges, n will always appear on one side. So we can assume that n is at the end of this line. So this is all.